Okay, let's go through calculating vertical jump height. Now, if we did this with a camera system, we could look at a person doing a jump. Let me try to draw a person here. This is why the person's still in contact with the ground. And if we used a camera, we could set up a Cartesian coordinate system consisting of X and Y positions. And then we would track some aspect of the person. And I'm going to say we're going to track the center mass, COM, the point where all mass seems to be concentrated. Center of gravity, center mass, same thing. And if this person does a jump, and I'll just do a vertical jump, this center mass would go up and then come back down, and the person would land and the center mass would be roughly the same height, okay, just as a starting point when we're discussing this. Now, if I was going to do a camera system, I could track where that center mass is at any moment in time. So I can create a table that would look like this. I'd have time data, I'd have X data, and I'd have Y data. So time 1, time 2, time 3, all the way up until the end of time. And then I'd have a corresponding X1 and a Y1. Let's say it's right there, okay? That would be X1, Y1, okay? And then I'd have X2, Y2, X3, Y3, and so forth, and so forth. And I'd have, the end X point and the end Y point. Now, when I have this type of data set, often what we do is we analyze one dimension at a time. Since we're interested in the vertical jump height, I'm only really going to be interested in, right now, the vertical dimension, the Y dimension. So from this plot, I can actually create two new plots, and I'm only going to be interested in one of them. I could have Y versus time, and I could have X versus time. And what I do is then I plot out my new set of coordinates for time 1, Y1. This is still a Cartesian coordinate system. And I would do the same thing if I'm doing X. I'm just going to put down here, X1, time 1, X1. Even though X is on the Y axis, time is on the X axis, and the horizontal position is on the Y axis. And then I would do this for each of the coordinates, T1, X1, T2, X2, T3, X3, all the way to the end. And same thing, T1, Y1, T2, Y2, T, and so forth. I'm only going to focus in on the vertical direction because we're interested in vertical jump. Okay, so let me redraw this. Oh, I'm marking up my paper. So I'm going to put Y versus time. And then right below that, I'm going to put velocity in the vertical direction. This is vertical. And versus time, same time axis. And then right below that, I'm going to put acceleration. These three kinematic parameters are all mathematically linked, and we should know the relationship between these three, and this is vertical. And I'm only going to concern myself with the flight phase of the jump. That is, I'm not going to concern myself when the person's in contact with the ground, so I'm not interested in this part. I'm only interested in the point that the person leaves the ground and then tracking the center mass at that point. And I'll just emphasize center mass right here. Center mass y, center mass velocity, center mass acceleration. Okay, so now I'm interested in the point that the person takes off, so I'm going to write take off, and the point where the person lands. Okay, I'm not interested in what happens after that point or what happens before this point. This is the moment the foot leaves the ground. This is the moment the foot touches the ground. I'm going to just draw those hash marks down below. So these things all line up in time. This is time. And let's start filling this in. Well, I have some other presentations on PVA and projectile motion. I'm going to jump right into that. We should know that when we track the flight phase of a projectile in the vertical dimension, we get a shape of a curve. I'm going to do the best I can. That looks like this. That's called a specific shape. It's a parabola. Very symmetrical on both sides. And when I do that, what I end up having for velocity is a velocity that starts off positive. It goes through 0 at the highest point and then ends at the same magnitude of velocity here, but in the negative direction. And so I get, I didn't do a very good job of connecting those. I'll make my dots bigger. A little fudge factor. And you get a straight line that looks like that. Well, that is, in words, a description that velocity is starting off high at takeoff and starts to slow down while moving upwards. You reach the highest point, and then velocity starts to speed up, moving downward. So this is all upward movement, this is all downward. Negative velocities are upward, positive velocities are upward, negative velocities are down. Okay, and when I do that, and I have this straight line, what I end up with is an acceleration plot that looks like this. And we should know that this is the slope. Acceleration is the slope of the velocity versus time plot. This is a negative slope. This is a negative acceleration. And when we're dealing with projectiles, we're dealing with an acceleration of negative 9.8 meters per second squared as the unit for acceleration. Meters per second for velocity and meters for center mass. And so when gravity is the only force acting on an object, acceleration will be constant. That means velocity will be constantly changing, and what that yields is a parabola as a position. Well, let's look at and you should be familiar with the equations of constant acceleration. And in this case, A is a constant. And if we go back to some calculus, and I'm not going to go through the details of it, but if we integrate this curve to get to this one, this is all mathematically related, well, we should know A equals delta V over delta T. If I rearrange this, delta V equals A times delta T, or if I break this out a little further, A delta T, final velocity minus initial velocity, or finally VF equals VI plus A delta T. And you should recognize this as one of your equations of constant acceleration. It's just the equation for acceleration. And all this is saying is that the final velocity is equal to the initial velocity plus the acceleration that's constant times delta T. All right, and now if we take this curve and integrate it, we actually get this shape up here. This parabola is a second order polynomial. And when we have a second order polynomial and we integrate this equation with respect to time, just like if we integrate this with respect to time, we get this equation. When we integrate this with respect to time, we get this equation. And I'll write it out this way. First, delta S, position, change in position, equals VIT plus 1/2 AT squared, or final position minus initial position equals VIT plus 1/2 AT squared. One more version of this, SF equals SI plus VIT plus 1/2 AT squared. This is another equation of constant acceleration. You should know this equation. And all this is saying is the final position is equal to the initial position plus the initial velocity times time plus 1/2 A, which is constant, times time squared. This is the equation we're going to use, we often use to calculate jump height. But what we do to make it even simpler is we have an instrument that measures simply flight time, how long a person is in the air. I'll make this a little thicker. Okay, we measure how long the person's in the air, and we call that delta T. But to use this equation, we take advantage of simplifying the equation a little bit more. At this point, this highest point, velocity is 0. And so often what we do conceptually is we calculate how far this object will drop, which ends up being delta S, when the initial velocity is 0. Why do we do that? Well, because that simplifies this equation. I get VI would go to 0 plus 1/2 AT squared. A is a constant, T would be half of this flight time because we're at the same height at takeoff versus landing. All right, so this is how we calculate jump height. Let me get another piece of paper here and write that equation out. SF equals SI plus VIT plus 1/2 AT squared. And when we do that, and we use the different instruments that are available in the lab, we actually calculate flight time. Right. Time equals T, but then we divide that by 2, or take half of that, when we are looking at the takeoff position and the landing position being the same height. Because this is very symmetrical, so whatever time happens here happens over here, and the apex of this is 0. So flight time is T, so to do jump time, we actually take 1/2 T. And then we also only look at the time to reach the apex, or if we just want to do it simpler, we're just for conceptual, we can identify that this velocity here is 0, and we are going to calculate this distance here. So we do VI is 0 meters per second, only dealing with half the problem. And then I simplify this equation to SF. Oh, and then if I also set SI to just be 0, just because I'm going to start at the origin of the XY, then I have simplified this equation to SF SI plus VIT plus 1/2 AT squared, but SF is now equal to 0 plus 0 plus 1/2 A, and this is 1/2 flight time squared. So now this is our equation. SF equals 1/2 A flight time divided by 2 squared. And this is the equation that different instruments use to calculate jump height. It's all predicated on this idea that takeoff and landing position are exactly the same. If these are not exactly the same, then we've got some more math that we actually have to deal with on this end. But we start with this idea when we're doing a group test, or we're doing a large group of people, that they're going to take off and land at the same time. Let me draw on that a little bit more. All right, I pre-drew a couple of stick figures, and this would be takeoff, and this would be landing. Now, if we just go ahead and identify the center of mass, and I haven't drawn the arms here on purpose, I'm going to say it's about there, COM, and it's about here at landing. Almost, for the most part, people are going to land in about the same position as takeoff in regards to the foot angle, the leg angle, the thigh angle, and so forth, even the trunk angle. For the most part, those positions are going to be pretty similar, or enough that we can do our calculation of final initial position being the same. The trick is the arms. What to do with the arms? Well, how do we land with during a jump? Typically we land with our arms down. Okay? If we tell someone to jump as high as you can, what actually happens, and you don't give them any instructions on what to do with their arms, what do? They usually take off with the arms up. Well, when that happens, that actually moves the center of mass up when the arms are up in this position. So now we have a situation that the center of mass is at this height at takeoff, but it's at this height at landing. And now we violated our calculations of jump height. So what do? Well, the easiest solution is to just tell someone, land the same way with your arms as takeoff. Okay, that's by itself is a little bit hard. So what we do is we tell people, put your hands on your hips and leave your hands on the hip as you jump upwards and as you land. And when they do that, we'll be close enough that the center of mass will be close to meeting our assumption that it's at the same height at takeoff versus landing. If they start using their arms, well, then center mass goes up. If they use the leg, like they do a single leg jump, and I'm going to draw the other leg in here. Well, that's pretty extreme, but well, what that does is also moves the center mass up, because now we have more mass upwards at takeoff. Now I'm taking off from 1 foot. That would mean to use our calculation we just did for jump height, I would need to land in this exact same posture, meaning I would have to land with 1 foot upwards and the arms upward. Without that, I'm actually going to have a situation where the center mass is going to be higher at takeoff than landing. All right, so what does that mean for our position? Well, what's happening, our instruments are not that smart. And so this is why vertical position versus time, this is 0. And if I make this my initial height at jump, and this is my initial, and then I land with the first situation where we take off and land with the same posture, hands on the hips, then my landing is going to be right here. Well, there's only one parabola that can fit those 2 points, and that's that. If instead I actually take off with a higher position, one of these, the box or the X, than landing, then I've got a situation where the height of takeoff is going to be higher than landing. And I'll just do it this way. Well, I'll do it the way, let's say the height of takeoff is up here, and then the landing is lower down here. Well, that doesn't work because now I've got a difference in height between this and this. And so really what happens is that our systems will think that this is here, and then because we're now going to be in the air longer, then I'm going to have a landing position all the way over here, and now I have one parabola that fits that, and I have a higher jump. Fictitiously. okay? Simply because my center of mass was higher at takeoff than at landing, okay? So going back to this graph here, we do not want this situation when we're trying to test jump height, because we're only trying to determine the height of the center of mass vertically as the person goes up and downwards. If we have a different position at takeoff than landing, our assumption in terms of how our instruments work, it will give an erroneous, it will give a jump height, but it won't be right, because our jump height is simply taking flight time divided that by 2, thinking that everything is symmetrical, but in reality, if I drew it out this way, this would go down to here. And in reality, this second half of this parabola is not symmetrical with this first half because I've got a lower position. So that's why I got to move it up here. I got to shift everything upward. So it's a little hard to draw, but that's what's happening, is that in essence this is the new 0 line. So you actually just shift this up, rotate that upwards, and you get this graph right here, which is going to be a higher apex, fictitiously. Okay. So if you can trick the system to have a longer flight time, you can trick the system to have a higher jump. And we've done that in the lab. It's easy to, just jump off sit off the instrument that's detecting contact with the ground, then jump back on, and you're increasing flight time. And the system doesn't know anything other than how long the object is not in contact with the map. So really what we're dealing with is when we're doing our jump heights, we're doing center of mass, vertical displacement, and we want the same, I ran out of room. We want the same height at landing as takeoff. If this is violated, then our instruments that measure flight time won't calculate jump height accurately. Now, the other reason why we put our hands on our hips is that allows us to figure out what the lower extremity is doing in terms of generating power to jump upwards. And so it's a nice evaluation of just the lower extremity. If I do allow the arms to move, which is naturally how we jump, well then I'm testing something else. I'm testing coordination of the ability to jump high. And so the type of test that you do and the instructions you give to the subject is really is going to determine how you're going to use that jump height. Either you're using jump height to represent a system coordination and the ability to generate the greatest force to jump as high as possible using both the upper body and the lower body coordinated together. Or if you're interested in just the lower extremity, then you're going to be focused on just the lower extremity, so you're going to eliminate the arms. When we do combine testing, it's a little mixture of both of those reasons, in that our instruments to measure jump height quickly really rely on just identifying that final and initial position are exactly the same, and therefore it's easier to say put your hands in your hips and then jump and land in the same posture. Okay, so that's going through jump height a little bit. Hopefully that helps and helps understand how the instruments work a little better. Thanks so much.